So I'm expecting you to give the biggest applause to Sonya before and after her talk. Thank you.
I am the last thing that stands between you and free beer. So that's a rough place to be. But it being the last talk of the day, I did want to thank the organizers of the conference. Putting on a conference is hard work. There is not a lot of in-person conferences here, so please express your gratitude to them. It's been a wonderful opportunity. All right. Primero, first things first. This talk was always meant to be a duet. Vlad and I co-developed this material. This would have been our second collaboration here at GSAS. Unfortunately, due to situation in the world, he couldn't be here today, so please wish him well, wish him to return to GSAS, and importantly, congratulate him on his recently published book. In the meantime, I am going to be doing this solo. This is me. My name is Sonya Natanzon. I am a software architect. I lead engineering teams, an experience I drew on heavily for this material. And another important experience, I tried to make things as simple as possible. We'll talk about complexity today. So when Vlad started writing his book that was just recently published, Balancing Coupling in Software Design, people would ask him, do you really need to write 300 pages to say that coupling is bad? I might have been one of those people. And his book is about things we know intuitively, but sometimes have a hard time defining clearly. Two of those things are complexity and modularity. Both describe systems. We could say that a system is complex, or that it's modular, or a bit of both. But before we go on, let's agree on what a system is. This is a great definition by Donella Meadows from her book, Thinking in Systems. She defines it as an interconnected set of elements that are coherently organized in a way that achieves something. In other words, a system has a set of components that interact to achieve a goal of that system. By that definition, systems are all around us. More importantly, in our domain of software engineering, we both interact with and design systems at every level of abstraction. Say you're working on a distributed system, microservices architecture. In it, microservices are components that are working together to achieve the overarching goal of a system. But what happens when you zoom into one of those microservices? What do you find inside? Inside, you're going to find namespaces or packages, depending on the tech stack that you're using, and those are working together in order to achieve the overarching functionality of a microservice. Further down, if we assume object-oriented language, you're going to find classes that are interacting to achieve a goal of a namespace. And even further down in classes, you're going to find methods and properties that are working together to achieve the goal of a class, making it a system at a lower scale. We know technical systems pretty well, but systems exist in a social context, not just technical one. And I would posit that the same definition by Donella Meadows applies. Social system has elements, they're interacting, they're working together to achieve a goal, but it's always easier to demonstrate this on the examples that are familiar to us. A school is a coherently organized set of elements that's interacting and working to achieve a goal, an education. Family is an organized set of units that is working together to achieve another goal, propagation, survival, protection, and so on. Is it coherently organized? It is a family after all, so not always, which gets at probably an important property of social systems. They're not always as nice and neat as we like them to be, but it's a system nonetheless. A software development organization and software enterprise is another social system, but with a few more caveats thrown in. Social structures in the enterprise are not always coherently organized. The goals of it are vague and changing. We know companies pivot, and the way you achieve those goals changes as well. And those caveats might exist because we haven't done software engineering for hundreds and thousands of years that we've had families and schooling, but perhaps they're just properties of a socio-technical system. There's one more important thing to know about systems, and it was best said by Edward Deming. A system, every system, is perfectly designed to get the result that it does. But why? Well, because it gets that result. So what result will you get if your technical system is complex? Or if your social system is not coherently organized? Is the result that your system is achieving perfectly now the one that you intended or desired? And how do you bring those two to be one and the same? So now that we agree on what a system is, let's talk a little bit about modularity. I bet we all want to design modular systems. But why? And what makes a system modular? That's an interesting question, and I want to start answering it by defining what a module is. And for that, we're going to go in a Wayback Machine to the time when the concept of modularity was first introduced in software engineering, the 1970s. And this is an excerpt from a book from 1970s that I recommend, which defines a module as an executable set of program statements, which is an old-timey way of saying a piece of code that meets the following three criteria. First, it needs to implement a functionality. So if you need two pieces of code that implement one functionality, they're not, strictly speaking, a module. Second, it needs to expose that functionality to the rest of the system so that the system can call it, meaning it should have a public interface. And last, it should have a potential to be independently compiled. Now, the word potential is important here. It may already be independently compiled, but in absence of that, it should have a potential to be. Following that definition, where do we find modules in software design? Well, microservice fits that definition pretty perfectly. Namespaces, also. Classes, same story. Methods, they're not usually independently compiled, but if they have a potential to be, they will also fit the definition of a module. So does that mean that modules are just components of a system? Well, that part's only half true. Modules are definitely components in the system, but it doesn't always work the other way around. Components are not always modules. It's all about the goals within a system. Remember that a system implements a goal, its functionality. Modular design expands that functionality to the system's potential future. In addition to implementing its current functional requirements, modular design accommodates implementing potential future changes for the system. The goal of modularity is to make future changes easy. That is why we want to design modular systems. If your system never needs to change, it doesn't need to be modular. It can remain a monolith until the day you sunset it. And of course, future goals of a system need to be reasonable. If you are converting your CRM system into a printer driver, not a reasonable goal. But if you're extending your CRM system to work with another communication protocol, perfectly reasonable goal. Of course, those are the kinds of systems we want to design, systems that are easy to change, that adapt to future business needs. Unfortunately, what we get with some regularity is the opposite, complex systems that are complex to change. To understand why that happens, we should understand what complexity is. And this definition I absolutely love. It's the epitome of this intuitive understanding of things. I know it when I see it. But in order for us to manage complexity, we need something a little more nuanced. And that more nuanced definition comes from Kinevin framework. That framework assists with decision-making, and it makes complexity a function of a relationship between cause and effect. Let's say you're making a change in your code, and you know exactly what the outcome will be. That is not a complex system. That is a clear or obvious system. Let's say you're making a change and you don't know what the outcome will be, but there's somebody you can ask, they will tell you, or you can do some analysis and have reasonable certainty that you know what the outcome will be. That's also not a complex system. In the lingo of Knevin, this is a complicated system. But now, let's say you're making a change and there's no one to ask. No amount of analysis will give you certainty of an outcome, and the only way for you to know what's going to happen is to make a change and observe the result, basically conduct an experiment. Well, then you're dealing in a complex system. There's plenty of examples of complexity in software engineering. Say you need to change a line of code, and you have no idea what's going to happen. I've seen those lines of code. Usually they can be broken down in like 5 to 10 other lines of code, but you go ahead and make a change anyway, compile it, run it, hope for the best. That's complexity. Or you make a change, you know what the outcome will be, and all of a sudden, a completely unrelated part of a system starts malfunctioning. That's complexity. Or you need to make a change to current requirements, but the design of a system makes it impossible for you to know which modules would you need to change in order to implement those. That's complexity. It's easy to blame this on system design, but complexity, this is not the only source of complexity. Complexity is also about us, about our cognitive abilities and limitations. There was a study done in the 50s that determined that we can comfortably process 7 plus or minus 2 units of information. That same study was repeated 50 years later, and the number went down to 4 plus or minus 1 units of information. So the trend isn't good. Either our brains are shrinking, or much more likely, our world is quite overwhelmed with information. There is a lot to process. The more of it is out there, the more cognitive overload and the more complexity we have to deal with. But complexity doesn't just exist in technical setting. It exists in social setting as well. And in it, you know it when you see it. It's worth, however, examining both manifestations of social complexity and its underlying causes. I worked with this project manager who, after 6 months of being at a company, told me, I have no idea where to go to get my problem solved. I've worked in much bigger organizations, and it was always clear to me how to navigate them. Here, I go to one group where I think is the right place, and they send me to another group, and they send me to another group, and so on. That's a manifestation of social complexity. And much like technical complexity, that one comes from bad design. In this case, bad organizational design. When I ask leaders who have this perceived bad organizational design, who basically show up with something like what this project manager struggled with, teams with ill-defined roles and responsibilities or unexpected roles and responsibilities. The question that I give them is, why does your organization look the way it does? And the answer I often get is, it has grown organically. As if there is a way to synthesize organization chemically. But just because you're growing something organically doesn't mean that you don't plant and weed and prune and shape and otherwise structure it. This garden has grown organically too. It was just much better taken care of. And remember that every system is perfectly designed to get the result that it does. So the difference in results should be pretty obvious. So why does this happen other than the aforementioned organic growth? Well, this project manager encountered teams whose names didn't reflect their functions or sometimes had way too many functions. The worst offender of this I've seen was a department that had a name that was made up of 6 letters, and each letter stood for a function, which is like 5 too many functions for a single department. Another one is responsibilities mapped to unexpected roles. If I go to a sales team and find out that they actually do marketing, I'm surprised and a little perplexed. But if I go to a data management team and find out that they write mobile apps, I am definitely very confused. How does that happen? If we take this team that has strange, unrelated, unexpected responsibilities, like a data team doing mobile apps, what could have happened is they were just perceived as more available at the time a critical project like a mobile app that was needed, and they just got it by sheer availability. They could have had somebody with the right skill set to implement it at the time. Or the thing that I observed the most is there were probably a high-performing team, the project was critical, and the company wanted to ensure success, so they just handed it to a team that had good track record of delivery. A microcosm of this is a helpful engineer who volunteers to do something in a time of need, only to be stuck with that thing forever. The more nefarious cause of this is personal ambition. Sometimes to get promoted, you need more scope, so you grab projects that you think will get you that promotion. Resume-driven development. We all want to have cool stuff on our resume, AI. So we get, I thought I wasn't going to use that word today, but it happened. So sometimes projects land in teams and people where we don't expect, so much harder to deal with. And as a matter of fact, the example of mobile app in a data management team, which, by the way, is a real example that I encountered, was exactly for that reason. It was the leader of that team was ambitious, wanted to get promoted, and grabbed a high-profile project. Actually, all examples here are real. I just changed the name to protect the innocent. All right, so the second manifestation of social complexity is this what just happened effect, which is what teams who had nothing to do with the work or decisions say when they get hit with a knock-on effect. That happens to teams that work pretty far downstream from core product development. It happens to teams that have user-facing components that synthesize work from a lot of other subsystems. And if you're lucky enough to work with a support team, it definitely happens a lot to the support team. Much like technical complexity is a function of bad design and our cognitive ability, social complexity is the same. In this case, cognitive ability refers to our ability to understand which parts of the social system are connected and how. Sometimes the social system is just too big to know. If you're familiar with the Dunbar number, it's a number of social connections that we can process at about the same time and realistically maintain. Lands at about 150. So some social systems are too big to know. At other times, it's lack of communication. Let's say one team is making a change, and then it gets audited, and the auditing team doesn't like the change. But the first team had no idea that audit process even existed, much less that it had very specific needs. And then at other times, it's silos. Silos were talked about today a little bit. Sometimes silos have good intentions behind them. Limit the team's cognitive load, allow them to operate independently and autonomously. I've seen different kinds. The worst one I've seen was a silo that was built around the team very intentionally by its leader in order to prevent others from seeing the team's continued failure. Sometimes it's just too hard to know how certain parts of a system are connected because they're connected in unexpected ways. Say you have two teams, completely different organizations, working independently, using the same commercial platform. That commercial platform has a vendor contract, only one vendor contract because it's more cost-effective that way, and that vendor contract is managed by one of the team's leads. That team doesn't need super high performance, so next time contract comes up for renewal, they negotiate good discount for throttled performance. Guess how the other team finds out about that? So even though those teams seemed very independent, they still had this connection through a vendor contract, very unexpected. And the last manifestation of social complexity that I want to talk about today is everything being slow. I have never met an executive who didn't think that their teams couldn't be doing something a little faster. I'm always a bit cautious about that. Executives see things at high level. Software engineering happens at low level, the lowest level, and you need to make space for details and complexities to emerge. However, there comes a point where it's no longer about the details, but about something else. Usually when executives complain of slowness, what they really mean is that new value is too slow to be delivered. If you think of it as your DORA metric, this is your lead time to change, that slows down, and it slows down without any relationship to the underlying technical complexity. Few reasons for that. Sometimes you just have to do things by the book. You have to comply with regulations, you have to make sure you fulfill InfoSec requirements, and so on. Unavoidable. Sometimes it's potentially avoidable general bureaucracy that grows over time, and that may or may not be applicable anymore. Maybe it's mitigating risks that no longer exist. Maybe it's dealing with error-prone human processes that have long been automated away. In any case, bureaucracy, just like that garden, needs periodic pruning. And sometimes it's too many connected or potentially connected components. We don't know which component connections still remain valid or important, so we have to trace all of these impacts through all of those potential connections and coordinate around everything. Unless you want to not worry about that what just happened effect that we talked about before. The biggest lead indicator for me of that type of slowness is the number of people that you have to tell that you're doing a software release. The bigger the number, the slower that release is going to be. So how do we steer our systems away from complexity and more toward modularity? Well, as you probably guessed, it has something to do with coupling. Imagine you have two components that are connected. Doesn't matter what they are, doesn't matter how they're connected. The fact that they're connected means that they're exchanging something. And that something is data. One component might ask for some information from another one, or it might instruct it to do something. But data is not really the most interesting thing that they're exchanging. There's a slightly different kind of energy to what they're sharing. And what they're sharing here is knowledge. There's many types of knowledge that components can share, and this integration strength model categorizes them into 4 different categories. The higher the integration strength, the more knowledge flows across the coupled component boundaries. The first one is what we call intrusive coupling. Let's say you built a module and I want to integrate with it, but instead of going through that nice public interface that you provided, I decide to use some implementation detail. The favorite of everybody is going directly to the database and grabbing what I want. That is quite intrusive. We're at implementation coupling. Alternatively, modules can share information about functional requirements. This happens in many cases, the most extreme of which would be something like you're migrating functionality from one system to another. And you need to run the new system simultaneously with the old one to make sure that nothing is broken. So you potentially have 2 modules that are implementing exactly the same business rules in 2 different systems. If you have inconsistent implementation, the system will behave erratically. So the reality of the situation is, if you have something like this, And if you have a change to functional requirements, you have to change it in 2 different places. So those modules will have to change simultaneously. You can have model coupling. So rather than functional requirements, modules can share information about the business domain that they're in. It's unrealistic for us to think that we can implement a sufficiently large business domain in a single module. Let's say you're dealing in a medical domain, and there you have patient chart, you have scheduling, you have procedures, you have laboratory tests. We pick and choose the portions of the domain implement them in different modules in order for us to accomplish the goals of the system that we're working on. Again, the practical implication of this is the more domain knowledge the modules are sharing, the more likely they will have to co-evolve. And last but not least, you can develop an integration contract. And that integration contract encapsulates all of the other information. It can encapsulate implementation details, functional requirements, domain models, without having to change. This type of coupling maximizes encapsulated knowledge and minimizes cascading changes and shared knowledge across the 2 components. But knowledge is not the only interesting attribute we should be paying attention to. The other interesting attribute is the dimension of distance, or physical space between coupled components. And that physical space exists at every level of abstraction. The lower the level, the less distance between them. The higher the level of abstraction, the more distance between coupled components. But what is the implication of implementing interrelated functionality at different distances? What do you think we get on that vertical axis? What we get is coordination, and that is coordination that we have to expend in order to implement changes at those various levels. Think about coupled statements and the coordination effort it takes to implement, probably single engineer who can coordinate themselves, versus coupled systems, which is probably a large project across 2 teams in different parts of organization with a lot of coordination effort and scheduling around them. This distance is going to inform the cost of a change, which is going to be proportional to that distance. Again, coupled statements, coupled systems. So if we take those 2 dimensions together and examine their effects, we can look at the combinations of the 2 to see what type of knowledge sharing and what type of behavior we see in the system. And we can start this by taking low integration strength over high distance. Here, because we have high distance, the cost of implementing changes is going to be high. But we have low shared knowledge, so the occurrence of those frequent changes is going to be pretty rare, minimizing all of those cascading changes. This is a type of relationship that we call loose coupling. And that relationship exists in organizations too. Let's say you have 2 teams, different organizations. One is happily building products, and one is dealing in data operations, tuning databases, doing backups, doing all sorts of stuff. They almost never have to interact in general. But let's say one of those products that a product team built suddenly starts producing a lot more data. Performance goes through the floor, interfering with backups, and now data operations team has to react. Is this a temporary spike? Is this a permanent change? What do we do about it? Likely resulting in a pretty hefty project in coordination with product team. But it happens quite rarely, so in general, your organizational structure is as good as it gets. Now let's take the opposite, high integration strength over low distance. Here we have high shared knowledge, lots of cascading changes. But because of the low distance, because the modules, related modules are sitting close together, the cost of implementing those cascading changes is minimized. This is the relationship that we call high cohesion. And surely enough, it reflects in organizations as well. Let's say you have a bunch of products. Those products interact with each other, they're interrelated, they impact each other when they change. And there's a single team that's building them and managing them. Well, because all of those changes are happening within a single team, they can coordinate amongst themselves, and the cost of those changes is less. Now, let's take low distance over low integration strength. Here, we have low cost cascading changes. We have low shared knowledge. And that sounds good. Low shared knowledge means low probability of cascading changes. But what often happens is we get many co-located, unrelated modules, resulting in local complexity. Whatever module hosts them, and whoever needs to work on that overarching module is going to have to make sense of those unrelated modules. So local complexity is a complexity of a single module, of its internals. And as you might have guessed, it very much reflects in the organizations. As a matter of fact, the first team I led was an embodiment of local complexity. And the way I found that out was I started building a roadmap for that team, and pretty quickly realized that it was 3 completely unrelated roadmaps. So the local complexity sat with me to try and figure out who works on what, managing people working on those separate roadmaps, and the components underneath. Last but not least, we have high integration strength over high distance. Here we have high cost of cascading changes. We have high shared knowledge. So what does that mean for us? Double whammy. Things are that much more difficult with frequent cascading changes, and that relationship is global complexity. Global complexity is a complexity of interactions within your system. So this is no longer a single module, it's interactions within the system. Your knowledge is flowing across long distances, causing a lot of cascading changes and taking a lot of that coordination cost. This is my favorite example of global complexity. You have 3 products, 3 systems, and 3 teams managing them. Your customer relationship management team, your order management team, and your customer portal team. Now, order management and customer portal both need to know about customers. That information comes from their CRM, but for reasons long lost to time, customer portal team, for some reason, is getting it through order management rather than directly from CRM team. So what happens when customer portal team wants to get one more piece of data or something new that the CRM team acquired? They have to go to order management team and ask them to implement the change that they probably don't need. So high shared knowledge, lots of cascading changes, big distance with high cost of implementing those changes. Not great. So how do we steer our system away from local and global complexity and move it towards high cohesion or loose coupling? Well, we need to balance the integration strength with distance, and we can represent it as strength XOR distance. If your integration strength is high, your distance should be low. That's high cohesion. If your integration strength is low, distance should be high. That's loose coupling. If both are low or both are high, the relationship that ends up existing is a complexity of some sort, either local or global. So how do we apply this in real life? Well, we start by minimizing integration strength as much as possible. And keep in mind that level can't always be lowest. We can't always have a nice contract. We'd like to, but can't always. Sometimes we have to share functional requirements, domain models, and so on. But once you got to the lowest level you think makes sense for your business, balance it out with distance. If you landed on low integration strength, put high distance. If you landed on high integration strength, then decrease the distance. Can we expand that to our social system? Let's say you have two components that have a lot of shared knowledge. This is your technical components. Lots of cascading changes and high distance, and you shrink the distance. Maybe you removed an intermediary, maybe you added a shared dependency. Great. But those components were being managed by two teams that somehow were coordinating those changes across. So if you made those changes to your components but didn't do anything about the social structure, what likely just happened is you introduced a new friction into your system. Your social boundaries are no longer aligned to the software that they are producing. Now, this friction is hard to live with. It does cause difficulties, but it can be resolved. And the way to resolve it is to apply the same formula to organization. First, we need to understand what shared knowledge exists and how to minimize that. Luckily for us, we've known for quite some time, since 1960s to be exact, how knowledge flows in the organizations, and importantly, what impact it has on the systems that we produce. And that's that information. I am pretty sure that if Conway's law is mentioned in a conference, everybody's required to drink, which luckily you'll be doing shortly. Everybody should know this by now. Organizations which design systems are constrained to produce designs which are copies of the communication structures in those organizations. And that is colloquially known as Conway's law. So once you understand those communication pathways and can't shrink shared knowledge any longer, balance it out with some distance. If you have low shared knowledge and low distance, the team that I worked with, increase the distance. The choices here is you can either distribute the components to the right teams or you can distribute the team. Look to create either high cohesion or loose coupling with either one of those moves. Now, once you've done that, you have to reinforce that. And the way to reinforce it is, actually, we have two ways to reinforce it. First way to reinforce it is a good team charter. You've now created some good boundaries, you reduced complexity, you have some modularity. You want to let both this team and everyone around them know what they will and won't be responsible for. A good team charter gives the team something to look at, and when new responsibilities show up or somebody volunteers for something, they can ask themselves, does this belong here, or will it ultimately increase the complexity if it lands here? The other way to reinforce is upskill the teams on technology. If there's one person or one team that knows a particular tech, it becomes really easy to dump all the work that requires that tech into that team, ignoring any kind of boundaries and ignoring any complexity that might arise for it. If you remove the technology barriers, it becomes a lot easier to keep the complexity down and keep your team's modularity. All right, so now the opposite. If you have high shared knowledge and high distance, you want to reduce the distance. First, if there is constant coordination between some teams, consider unifying those teams. Coordination within a single team is always, always easier than across even the closest teams. For the teams that have frequent cascading changes, consider putting them under the same leadership or into the same organization. It usually smooths out communication flow. You have glue people that reside in the organization that will carry information about those cascading changes, making them a little bit faster and a little bit smoother. If you think about how you learn in your organization about who do you find out first? First, you get to learn about what's happening in your team. That's your team meeting, then your department, and then maybe sometime you find out about what happens in other departments. That's your Conway's law at work. So having teams closer together in the same leadership is going to facilitate a lot more of that communication. Last but not least, standardized processes within the organization that have cascading changes. If all teams have different processes, that is just more friction. And I don't care what those processes are: communication, software deployment, approval, whatever processes exist, if you make them all the same, it will go a lot faster team to team. And notice a lot of these things are addressing that very visible slowness manifestation of social complexity. So, you've done this really nice thing. You took your architecture and you simplified it. And then you used Conway's law to adapt your organization, to adapt its boundaries to your newly changed architecture, introducing that modularity. Could you do the inverse? Could you use Conway's law to structure your organizational boundaries in a modular way and have your architecture follow suit? You can. And this is what is called an inverse Conway maneuver. You are shaping your organization in a way that you want to shape your architecture and how you want your architecture to emerge from it. My experience with it is it works best in a greenfield systems. For existing systems, before you execute on an inverse Conway maneuver, ensure that it will give you the reduction of complexity that you want and improved modularity. When you execute that maneuver, make sure that you allow for some time and space for your technology to catch up. Otherwise, that constant friction is going to continue to exist. For example, do you remember this high cohesion organization? Lots of products. Products are very interrelated. They have a lot of cascading changes managed by one team. Well, it was decided that we need faster product development, and that faster product development will be better facilitated by small teams that are dedicated to individual products. Makes sense, right? Very streamlined teams, follows team topologies. So the team was broken up into this individual product-focused teams. However, it was not well understood by the deciders just how interconnected those products were, just how much they relied on the underlying commercial platform and its capabilities and limitations to be separated out. And more importantly, time was not given to them to have the technology catch up to that separation and introduce the appropriate distance. So the inverse Conway maneuver happened, but the same in technology didn't quite catch up. It was expected that as soon as the organizational move is done, things are going to go faster. So what was the result? Well, the result was very predictable. Remember that every system is perfectly designed to get the result that it does. The need to understand what the other teams are doing and how the other products are developing never really went away. The new and separate workflows that emerged for each product over time became a burden to the customers, and many different ways of implementing the same thing became a source of pretty constant bugs for engineers. The real important impact, though, is even though for a time it seemed like things were going faster, the coordination effort required increased so much that it ate up all the gains of that fast development. So, where does that leave us? First important thing is organizational and technological complexity and modularity are going to be mirrors of each other. If one is displaying a particular type of complexity, so will the other one. Second, similar methods and levers can be used to adjust both. We could use those concepts of shared knowledge and distance in order to move the systems away from local or global complexity and more towards high cohesion or loose coupling. The last and very important one is organizational and technological changes have to happen either simultaneously or in close proximity to each other. Otherwise, you're going to live with a lot of friction and a lot of tension between the two. Now, tension always, you can't live under tension forever. Tension seeks resolution, and it will be resolved. And in my experience, what gives in most often is the technology. It's just so much easier to change technology and organize it around the human social boundaries than the other way around, that it almost always happens. If you're wondering where some of your system bad design is coming from, examine the evolution of the teams that built it, and I bet you're going to be able to trace it into it. Remember why we want to design modular systems in the first place. It is so we can make future changes easier. Well, having a social modularity that works in concert with technical modularity is going to reinforce it and allow it not to devolve back into complexity. And that's going to make your future changes easier. Final disclaimer. Social systems are not as nice and neat as technical systems. We are dealing with people, after all. They have their own ambitions and motivations. Before you change any system, seek to learn how it got to the way that it is. All right, thank you.
Thank you very much, Sonia. We have some time left for a couple of questions. Are you ready?
Sure.
Let's go for it. So, do you know any fitness functions that address typical complexity issues? I am aware that there are many aspects of complexity, but maybe there are a few addressing different topics.
So, fitness functions. Neil talked about them a little bit. There's cyclometric complexity, all of those fitness functions, but I'm going to give a slightly different answer and be a little glib about it. I am the fitness function. Remember that complexity exists for humans. Somebody said that AI isn't going to care, we'll do away with compilers. So if somebody tries to explain something to me, or if I'm looking at it and I can't understand it, I think we failed the fitness function. It's for humans.
It's a great answer. So, what tools does an architect have at his disposal to ensure that a system is modular, and that when it evolves, it remains modular and maintainable?
So the question is about tools to keep things modular. To be very, very frank, I am not the person to ask about tools. I go by experience. If I can change things without a lot of pain, we talked a little bit about what issues exist with non-modular system, what complexity looks like. To me, the tool is I'm able to understand it and change it. I don't think there's anything that I've seen in the software that helps me automatically.
Obviously. And we have a specific question here about BAPO, B-A-P-O. I don't know if you know what this is. Business Architecture Process Organization.
Oh, okay.
Yeah, what do you think about it, basically?
So, business architecture and process architecture is important. In order for you to build a system, you need to understand what's the use and how it's going to be used. What's the value that you're going to get? I'll give you maybe one recent example that I encountered. There was a change being introduced in the system, and it felt very wrong to me, and I started asking, why are we making this change? And what I realized pretty quickly is the engineers that were working on it didn't quite understand what it's going to be for. What I asked them to do is to go to the users and to go to a product manager and come back to me and explain the business case and have it drawn out together with a process diagram. That act alone helped them really go deep and nail what they're doing, and they adjusted. But without understanding the business use case and the business value, I don't think they can be successful. So super important.
Great. And the final question, and this is quite a way to end the conference. What if the tech leads are defensive about any organizational changes?
So this is a tough one, and I will say this. I've been in a very privileged role of being able to change organizational structures. And it does take a lot of mental fortitude and emotional strength to do that. It's a hard thing to do. That change, like moving people around, is a hard change. I understand defensiveness. I've seen it. I think it helps to show what value we're going to get and really show them where they're going to go from there. I think once the change is implemented and adapted, lots of growth can happen. And to me, that's the way to overcome it, is to show what growth can come of it.
Thanks a lot, Sonya. Thank you.